Hello, folks. I'd like to take a few moments to try problems 4 and 5 in problem set number 5.1. I'm going to start with number 5 because that's where my spot is. These are static torque problems where some variety of torques are being exerted around a pivot point, and as we will see, how we define pivot point, it can be chosen wisely. So we've got a uniform bridge, 20 meters long. All right, so here is a bridge of some length, 20 meters long, and weighing 4 times 10 to the 5th newtons. All right, that by itself, what that tells me, I'm not told anything about some exotic mass distribution, so I can assume that the center of mass of the bridge itself is or can be represented at its physical center. So that is going to be 10 meters from the end of a 20-meter long bridge. So we've got the force of the bridge at that point. It's supported by 2 pillars, 3 meters in from each end. So I've got a pillar here and a pillar here. And each of those, of course, is going to exert an upward force. And we're told that a 1.96 times 10 to the 3rd kilogram car is parked 8 meters from one end of the bridge. And it doesn't specify. And so I'll just put the car here. So if the car is going to go right here, I'm just going to draw a rectangle for a car. And that, of course, its force is going to be downward. So we've got the force of the car downward. How much force does each pillar exert? All right, well, we've got 4 forces, which means depending on how we configure our formula, we could have as many as 4 torques. But here's the thing about choosing your point of rotation. This thing isn't rotating. So no matter how you consider it, by any calculation, all of the torques are balanced. All of the torques have to add up to 0. So that allows us to choose our rotation point, basically our imaginary rotation point, cleverly. And by clever, I mean I'm going to choose it to be this spot right here. I suppose, if we were not as clever, we could choose it to be around one of the ends of the thing. But in that case, let's see, I'll label some of these things. We got force 1 and force 2, the force of the pillars, and the forces of the car and the bridge itself trying to rotate this bridge, or downward forces. If we chose the point of rotation to be the far end, then each of these 4 forces could conceivably exert a torque about this point. But because we don't know either this force or this force, that would leave us with 2 unknowns and yet only 1 equation. So that is less appealing. So what we're going to do is we're going to instead place the point of rotation about there, so that F1, R1, well, R1, how far away from the pivot point is that force being exerted? Well, R1 is 0, so the torque that is exerting is 0. So it removes one of the terms from our equation. So what that leaves is for us to solve for force number 2. So the grand total of the torques, starting from this point in our thought process, there's going to be 0, and we've got 3 torques. As measured from this axis right here, we were told that the car is 8 meters in from the end, but the pillar is 3 meters in from the end. So between the pillar and the car, that's 5 meters. So we've got the force of the car times its radius. Now, keep in mind, the force of the car itself is, well, look at this. We're given the mass of the car. So the force of the car, sort of off to the side here, is the mass of the car times g. Right? Can't forget to multiply by gravity. So we've got m of a car times g times where that is, mgr, force times r. So that's the car, and that is going to rotate this clockwise. So according to our convention, clockwise is negative, so that would be a negative torque. The bridge's own weight is also going to rotate this clockwise if it were hinged at the left-hand pillar. So that's also a negative torque. We got force of bridge times its radius of bridge. And it's at the center of the bridge, which would be at 10 meters from the end, but measured from the pillar, that's going to be 7 meters. And then force number 2, the other pillar, is generating a counterclockwise torque, or essentially balancing. If the car and the bridge are trying to rotate this span clockwise, then the pillar is preventing that. So it's a counterclockwise torque, so that's positive. So we got F2 times R2, wherever that is. So now it's just a matter of plugging in values that we know. The mass of the car was 1.96 times 10 to the third times gravity, so that's 10 times its r, the radius of the car, which we had said earlier was, that's 8 from the end and away from 3. I think it was 5 meters. Got that right. Negative minus, so this is all equal to 0, minus the bridge, which is at the 10-meter location, but as measured from the pillar, that's only going to be 7. So the weight of the bridge is 4 times 10 to the 5th times its location, which is 7, plus the force exerted by that pillar. That's what we want to solve, but we do know where the pillar is. It's going to be, it's 3 in from the end, and the other one is 3 in from the end, and the whole thing's 20, so it's going to be 14 meters away from the left-hand pivot point. So at that point, it's number crunching. 1.96 times 10 to the third times 10 times 5 is 98,000 minus 4 times 10 to the 5th times 7. So it's 200. I got that right? I guess that makes sense. Bridge should probably be heavier than the cars going across it. 280. 28 with a bunch of zeros, 5 zeros. 1, 2, 3, 4, 5. Plus F2 times 14. So we've got, on the left-hand side, we got 2,898,000 on the left-hand side, and on the right-hand side, we've got F2 times 14. So divide both sides by 14, and we get F2 equals 207,000 newtons. Did I get that right? Who knows? There's no answer there. Basically, we repeat that process, just flipping all of our perspective over to the right-hand side. Duplicate. So instead of placing our pivot at the left-hand pillar, we're going to place our pivot at the right-hand pillar and repeat that whole thing. So I'm not going to spend time to do all of the algebra out, but suffice to say that we still have the force of the bridge, we have the force of the car, and we know the distance that all those things are away from the pivot point. So you could repeat and go the other way. Oh, I will actually throw in an alternate approach. So certainly we could reverse the whole thing and use torque. Alternatively, we could also recognize that this bridge itself as a mass is not accelerating in any way. Not only is it not rotating, but it's not accelerating up or down. So that tells us that the sum of the forces in the y direction have to be 0. Well, what forces are in the y direction? Well, we've got force 1, that's positive. We got force 2, that's positive. And we got the force of the car downward, and we've got the force of the bridge downward. And all of those up forces and down forces have to add up to 0. And so once we've solved the first half of the problem, we've solved for F2 already, and we know the force of the car and we know the force of the bridge. Well, that only leaves one thing left to solve. So arguably, once you've done torque once in this problem, you don't necessarily need to do it a second time, because you can rely on the sum of forces in a straight line adding up to 0. All right, problem number 4. A uniform, it's a good word to have, 5 meter long horizontal rod All right, we've got a rod, horizontal beam that weighs 315 newtons. All right, I'm going to pause right there. All right, it's a uniform. So that tells me that its center of mass is where we consider all of the force to be acting. So we got 315 newtons acting there. So we've got the, it's called a beam. All right, so the force of the beam is 315 newtons, and the radius of the beam, or so to speak, the location where that force is being exerted is, I'm going to say, at 2.5 meters as measured from the left-hand side. Now, in an example like this, again, it's in equilibrium, so you theoretically could pick the rotation point to be anywhere, but for a thing that actually, like, visually, mentally could rotate, it kind of makes sense to pick the point that where it's actually probably going to rotate. It's just, you know, a little more intuitive to think of it that way. And so it could conceivably rotate from the end, especially if the cable snapped, it's going to just topple down from where it's attached to the wall. So as measured from that point, the weight of the beam itself is exerting itself at 2.5 meters from the end. It's connected by a pin that allows it to rotate. Oh, good. You know, it's good to read all the words. Its far end is supported by a cable that makes an angle of 53 degrees with the horizontal. So that angle right there is 53 degrees. And, you know, daredevil person is standing 1.5 meters from the pin. Somebody's decided to just walk along this flagpole. A 545 Newton person is standing 1.5 meters from the pin. Thank you very much. We'll have to call the police to address this. 545 newtons is going to be exerted there. So the force of the person is 545 newtons at a radius of 1.5 meters. We would need to find the force in the cable that will prevent this whole thing from falling, and the force exerted on the beam by the wall. I don't know why R is there. So let's just think for a moment what this cable is doing. Sure, this cable is exerting a, call this the big T, tension. This cable is exerting a tension that is perpendicular to the beam, but because the tension's at an angle, it's also exerting a tension that is parallel to the beam, essentially pulling it into the wall. It is, you know, if the wall were made of clay, the beam would slowly kind of work its way into the wall. So the wall itself has to be rigid enough to push back on the beam so that the beam doesn't just immerse itself into the wall. So those are the two things we want to find, or at least they're connected to what we want to find. So let's do the tension first. So we've got, let's see, 1, 2, 3 torques about this point. There are 3 forces at some distance away from the point of rotation. So the net torque is going to be 0, and that's going to be the force of the person times their location, and they are going to be trying to rotate this thing clockwise, so that would be a negative torque applied by them. We've got the force of the beam itself, which is also going to be a clockwise torque, force of the beam times R beam, plus the force of tension perpendicular times its R. Why the perpendicular? Well, as I think we've talked about in class, if there's a force exerted in this direction and this direction, the force that is along the direction of the beam that would go through a line of action through the access point, that's not going to provide or prevent or have anything to do with the rotation of the thing. So as far as torques go, only the perpendicular component of the force is going to have any impact on the rotation of the thing. And so this tells us that we need an expression for force of the force of tension perpendicular. Well, we've been told that the force is acting at an angle, and so this tension, if I could break this tension into a parallel component, tension parallel and tension perpendicular, well, this is our angle right here. So the perpendicular tension is going to be whatever the full tension is times the sine of the angle. It's the opposite side of this right triangle. So T perpendicular is T sine theta. So let's put this together. We've got negative force of the person, which is 545, located at 1.5 meters, minus the force of the bridge, which is 315 newtons, located at 2.5 meters, plus T sine theta, which we know is 53 degrees, times its location. Where is it? Cable horizontal. I guess it doesn't explicitly say this, but I think we're led to assume that it's at the end of the beam. So let's say it's 5 meters. Sine of 53 is one of those convenient angles where it's a nice little fraction. So we've got, let's see, 545 times 1.5. Move those to the other side. So that's 817.5 plus 315 times 2.5 is 787.5 equals T times 0.8 times 5. So I can solve for the tension. Divided by. So I get tension is 401.25 newtons. That's the tension overall. That's the whole tension. If I were so inclined, I could break that back down and find the tension in the y direction, but kind of don't need to. It's already accounted for. But I still do need to know the force that the wall is providing inward. And so here's where I consider the forces in the x direction. This beam is in balance. It is neither accelerating or decelerating horizontally. And there is a tension parallel, tension in the x direction pushing it into the wall, and there's a force from the wall pushing back, so the beam doesn't go anywhere. And, well, that's just the sum of the forces in the x direction. This part's arguably a lot simpler. We've got the force of the wall to the right minus the tension parallel to the left. Those two add up to 0. So the force of the wall is going to equal the tension in the parallel direction, which is going to be the tension times cosine of theta. And so the force of the wall is going to equal 400 times cosine of 53 degrees, which is going to be 0.6 times I got this right? Oh, got it. Right, I forgot a piece. Didn't think through the whole thing. Yeah, let's keep going. So that's going to be 400 cos 53, 400 cos 53. So that's going to be 240.7 newtons. And you're thinking, well, that doesn't equal what the answer said. You're right. And that's because, this is the part I forgot to think about ahead of time, that pin isn't only holding this to the right, that pin is also holding this thing up. Because, you got these things weighing it down. If this was a slippery wall and there was no pin there, the beam could slip out from against the wall. So the wall itself, we got the force of the wall parallel to the beam, and we got the force of the wall perpendicular to the beam. So we got another piece to find parallel. All right, so, well, it doesn't make it that much harder. We just have to address the sum of the forces in the y direction. The force of the wall perpendicular to the beam, up and down, is going to is up. And, well, what forces do we have acting downward on it? We've got the force of the person down, we've got the force of the beam's own weight down, and we've got the tension perpendicular. We've got that y component of the tension upward. So the force of the wall plus the tension upward minus the force of the person minus the force of the beam, all those are in equilibrium. So the force of the wall is plus t perpendicular, which is going to be 400. I'm using rounding now. 400 sine 53 minus the person, which was 545, minus the bridge, which is 315. All those add up to 0. So the force of the wall perpendicular to the beam is going to equal 545 plus 315 minus 400 sine 53, 540. There's where 540 newtons. And all right, so there's 540 newtons this way. Looking over here on the left, 540 newtons this way, and 240 newtons this way. And so then we've got to put those together. We've got 240 this way, 540 this way. And so what we're looking for really in the final end is the force of the wall, which would be the Pythagorean theorem of those two things. Force of the wall is going to equal 540 squared plus 240 squared, square root of all that stuff. Force of the wall would be 540 squared plus 240 squared, square root of is 591 newtons. All right. Whew, yeah, it's a lot. It's a lot of steps, but each of the steps is completely based in things that we have done and hopefully are familiar with. Particularly the some of the forces in the y, some of the forces in the x, but the new piece is recognizing the torque. So essentially, it adds a third equation to our equilibrium toolbox. Everything in every direction is in equilibrium in this problem, and we can generate a formula which conveys that. So thank you for going on this ride with me. Have a good day.